Welcome to our second USACM Energy and Earth Systems Technical Thrust Area monthly webinar this fall. So just to say a few words about this technical thrust area that's organizing the webinars. So we're a part of the USACM, the US Association for Computational Mathematics. We cover a variety of topics such as climate and earth system modeling, climate couplings, geomechanics, wind, solar, nuclear energy, carbon sequestration, capture and storage, and oil gas recovery. And I would encourage folks to join the TTA, which is free if you're a USACM member. And if you're a USACM member, you get discounts to various conferences and workshops we organize. So there's a benefit there. We also have a LinkedIn page, so you can follow that to get up to date on updates on activities that we're doing. And so just to say a little bit about why is this not advancing? Here we go. The webinar series. So this fall's webinar series is featuring postdoc and early career researchers. So today we had Professor Ruby Few from Caltech a few weeks ago. Today we have Dr. Rachael Alfant, who I'll introduce on the, after this. And then we also have two more speakers, one on Tuesday, November 11th, Dr. William Correa-Reduns from Johns Hopkins, who will talk about wind modeling, and Dr. Nicola Retz from UT Austin, who will talk about digital twins for ice sheets. And we will be recording this webinar, so if you want to watch it after, or know someone who wants to watch it after, feel free to share it. It'll be posted on our main TTA site. So let me stop sharing, and you can, I think, go ahead, Rachel, and try to share. So let me introduce Dr. Rachael Alfant. So Rachel is a postdoctoral appointee here at Sandia National Labs, which is where I am, in the discrete math and optimization department. She works on optimization under uncertainty applied to power systems, in particular, how it relates to resiliency, to extreme weather events, cyber attacks, and rising electricity demands. She has a PhD from Rice University in computational math and operations research, and a bachelor's in mathematics from the University of Chicago. And she has served in several kind of outreach groups. She currently serves as a mentoring and outreach liaison for the Informs Forum for Women in Operations Research and Management Sciences. She was previously the vice president and president of the Rice University chapters of the Association of Women in Mathematics and SIAM, respectively. So with that, I'll go ahead and hand it over to Rachel, who will talk about performant optimization of power systems, resiliency, operations, and planning.
Awesome. Thank you so much for the introduction, Arena, and thank you everyone so much for being here today. My name is Rachael Alfant. I'm a postdoc in the Discrete Math and Optimization Department within the Center for Computing Research here at Sandia National Labs. And today I'm going to be talking about several projects that we're working on related to resiliency, operations, and planning in the context of power grids. Oh, and unfortunately, I can't see the chat from my screen, but I will be pausing from time to time, just to make sure, like whether or not there are any questions, and I'll also leave room, at the end of the talk for questions. So before I begin, I want to acknowledge that all of this work that I'm talking about today is done in collaboration with many, many people, including Zach Kilwine, Bill Hart, Tushar Gunda, Nicole Jackson, and Kyle Schofield from Sandia National Labs, as well as Matthew Veens and Georgia Stinchfield, who are PhD students at UW-Madison and Carnegie Mellon University, who are year-long interns at Sandia. So to provide some context, power grids manage the transportation of electricity from power plants to customers. And in the United States, there are over 642,000 miles of high voltage transmission lines, as well as over 6.3 million miles of local distribution lines. So this is a very, very large network, and it has aptly been called the greatest engineering achievement of the 20th century. So there are a few different reasons why power grid planning and optimization is so complex. First are that there are multiple sources of uncertainty often introduced into these types of problems. So for example, there can be uncertainty in loads or future electricity demands. And there can also be uncertainty in renewable energy generation. So if you think about wind and solar, for example, the amount of energy generated from these can be very dependent on kind of the ambient weather conditions. There are also multiple potential vulnerabilities that can be introduced into power grids in the form of deliberate cyber attacks or extreme weather events. So, somewhat recently in 2021, we saw that the entire state of Texas lost power for about a full week because of a winter storm. And so, these events can be very devastating on the power grid. And oftentimes, a lot of these problems concern multiple timescales from day to day to years out planning in the same type of problem. And also, this planning of out years forces us to make assumptions about what the future looks like in 5 to 10 to 15 years. And it's difficult to know what the effects of those assumptions are. And finally, like I said before, there are an enormous number of components and interconnections that make these problems very large and often difficult to solve. And if you are curious about kind of modern day problems that the power grid is facing, NPR's Shortwave podcast did a pretty great episode on this called What's Plaguing America's Power Grid. That's only 14 minutes long, and I would highly recommend that. So, to provide an outline for the projects I'm going to be talking about today, firstly, I'm going to be talking about two projects related to resiliency for power systems, including generation and transmission expansion planning, or GTEP for short, for resilience to compound hazards, as well as quantifying resiliency with a Python package called Pyrox. And then I'll be pivoting to a project focused on stochastic programming, and in particular related to its application to accelerating algorithms for day-ahead scheduling of generators. So to start off with resiliency for power systems, oftentimes when we talk about resiliency in the context of power grids, we're talking about the ability to prepare for, adapt to, remain reliable through, withstand, recover rapidly from, and harden the system against high impact, low frequency events. And these high impact, low frequency events can be, for example, extreme weather events that are presenting novel challenges to grid resiliency. So, for example, extreme heat can decrease battery efficiency, which can lead to underperformance of the batteries when they're needed the most, because oftentimes during an extreme heat wave, the demand for electricity skyrockets. And so this kind of underscores the need to quantify grid resiliency under different hazard scenarios, and particularly compound hazard scenarios. So I'm going to be talking a lot about compound hazard scenarios in this talk, and what I mean by that is when two events are either co-occurring or occurring at the same time, or when they happen one after another. So for example, we can have a wildfire and a cyber attack occurring at the same time, and we can also have a flood immediately following a wildfire. So to start off with wildfire and flooding, so this can be kind of counterintuitive, but oftentimes what can happen is after a wildfire, all of these water repellent compounds can rise up above the subsurface soil and make it harder for the ground to absorb water. So this can cause things like flash flooding immediately following a wildfire. And so some relevant questions that we want to answer here are: what are the effects of compound hazards on power grid resiliency? How can we quantify these effects? And how can expansion planning improve resilience to these events? And I'm going to be talking more about expansion planning in this next slide. So when we talk about capacity expansion planning, what we're talking about is the strategic planning of long-term investment decisions for power systems infrastructure. So these investment decisions can include anything from whether or not we want to underground a line, or whether or not we want to install a line, or if we want to install a certain type of generator and where we want to install it. And so this first project I'm going to be talking about is related to expansion planning. And in particular, we wanted to generate investment plans as solutions to these capacity expansion planning optimization problems under three different cases. So the first case that we want to optimize for is the case in which we assume that no power outages occur. So this is kind of our baseline default case. In our second case, we want to consider that some outages will occur. So in this case, we're optimizing under the assumption that kind of moderate outages occur, but nothing very widespread. And finally, in this third case, we want to optimize our expansion planning model under the assumption that severe outages will occur. So these are widespread outages. And so we use the IDSG Python package in order to model and solve our expansion planning model. And the ways in which our three optimization problems differ is that in our first problem, so in the case that no outages occur, we use 4 representative days, each day representing a season of the year. And so these representative days are meant to kind of represent the everyday conditions that the grid might encounter throughout the year. So in our first case, we just essentially have 1 from each season of the year represented. In our second case, we have the same 4 days plus an extra representative day, and this is a day in which moderate outages do occur. And so we have that day also represented that we're optimizing for. And finally, in our third case, we have the same 4 representative days that are in the no outages case, but we add in a 5th day in which severe outages occur. And the way that we select this representative day is through using a Markov random field method. So a Markov random field is a network of random variables represented by an undirected graph. And so in this case, we use Texas as our exemplar. And so each of the nodes in the graph represents a county in Texas. And the nodes are connected by an arc if the counties are adjacent to each other. And the compound hazard that we consider is a wildfire followed by a flood. And we use PM 2.5 data as our wildfire proxy, where PM 2.5 is kind of the particulate matter that you find in wildfire smoke. And we use precipitation data as our flooding proxy. And then so using this Markov random field, we find the representative days that we want to include in our moderate to severe outage cases. And so we solve 3 different optimization problems corresponding to the 3 cases. Where here on the very left, we have our generation mix generated after our optimizing our no outage scenario. And in the middle, we have our moderate outage generation mix. And then to the right, we have our severe outage generation mix. So for each of these plots on the x-axis is our investment year. So we consider 2025, 2030, and 2035 as our investment years. And on the y-axis is our nameplate capacity. So this is essentially the maximum capacity that we could theoretically generate if we were to make these investments. And so I summarize some of these results in the next slide because this can be a little bit difficult to see. But essentially, nuclear and coal, we can tell that those don't really change across these 3 scenarios. So whether or not there are outages or not doesn't seem to affect the investments we make in nuclear and coal. However, we do see differences in natural gas, wind, and solar investment, namely that there are large increases in natural gas investments by 2030 with minor additional increases by 2035 across all 3 cases. And also we see slightly less natural gas investment for the severe outage case than in the no outage case, and slightly more for the moderate outage case. So what this indicates is that the investments made in the moderate outage case were actually unable to prevent as much load shed as the investments made in the severe case. In terms of wind and solar, we actually see much greater investment in these in the moderate and severe cases, and also large initial investments to meet demand, which spike over the next 5 years, with some retired in 2035 across all scenarios. So what this indicates is that continued investment reflects benefits to resilience afforded by a broader generation mix, and also that wind and solar play a much more pivotal role when we consider outages.
Rachel, can I ask a question
Yes.
here? So when you're talking about outages, what's causing these outages and so are you talking about power plants?
These
Going
are
out of operation?
These are power outages reported by customers.
Okay.
Is this related, because you were talking about the wildfire followed by a flood?
Mhm.
So is that related to this, or that was just an example?
Yes, so this is, we're considering these investment plans developed as a result of a wildfire following a flood being the thing that causes the power outage.
So that has to happen a certain number of times, I guess, or?
We looked at it over the course of a day because we use kind of the representative days as proxies for like the three different cases. And then so we essentially used, we took the day with the most hours of outages, I believe.
Well, it just seems like if it happens once a year, right? Like that's not going to impact the investment. It would only impact the investment if it's a recurring thing, right? Like if it happens a bunch of times or a bunch of years. I
Yeah.
would think.
So like the representative day is essentially meant to be kind of like a proxy for like outages generally. So like even if it's just like one day in the optimization model, that's kind of a day that reflects conditions in which an outage occurs. So it can be kind of generalized to other days in which outages might occur.
I see.
But yeah, thank you. That's a great question.
And is there anything like particular about Texas, the example that you're considering?
Yeah, great question. So we do use Texas a lot because it's the only state that has its own kind of isolated power grid. It's managed by ERCOT and it's not connected to any of the other states. And there's also like a few different synthetic data sets that we can use for the state of Texas.
So yeah, one more question as a follow-up to my first question. So I'm trying to understand why wind and solar, for example, you see a difference in the investments depending on the scenarios. So if you have more outages, it looks like you need to invest more in wind and solar. Is that because they're more like local sources of power rather than, let's say, other energy sources?
Yeah, that's a great question. So we can kind of hypothesize that the increased investment in wind and solar kind of reflects a shift towards renewable energy being kind of like when on days in which some of the other standard sources that we have are struggling, like for example, if we don't have enough like natural gas, coal is kind of decreasing also, then these kind of newer sources of energy can kind of pick up and kick in and kind of manage that for us. But there is more research that needs to be done in this, and particularly, I think on this slide actually. Yeah, so we need additional research to assess why there's a higher priority for solar relative to wind and natural gas, particularly in the severe outage case.
I would imagine it would depend on the location, because like
Yes.
Texas has a lot of wind and a lot of sunny
Definitely.
days. Like if you're in Alaska or something, the
Definitely.
solar help you, especially in winter. But
That's a good point. Yeah. And I think ERCOT, the kind of organization that manages the Texas power grid, has been making more recent investments into wind and solar. So that might also be factoring in.
Okay, thank you.
Yeah, thank you for the questions. And so some key takeaways from this specific project are one, that significant increase in generation capacity is needed within the next 5 years, and that modeling impacts for compound hazards on power systems is critical for security and resiliency. And there's also a need to improve grid damage modeling in future work. And there is more information available. So this work was accepted as part of the 2025 Resilience Week proceedings. So if you are curious, please feel free to check that out. It's called Generation and Transmission Expansion Planning for Resilience to Compound Hazards. So next I'll be talking about quantifying resiliency with PyROX. And again, here we use the case study of Texas and specifically the synthetic 2000 bus grid network modeled after the ERCOT region. And so in the right, you can see these are the counties that are highlighted in blue. So this is most of Texas. And so we use a package called egret, which is a Python-based package for solving unit commitment and economic dispatch or optimal power flow problems, and also a Python library called PyROX for quantifying and analyzing resilience of complex systems. And so in this case, we consider 4 different scenarios. Our first scenario is just this baseline scenario where this is just standard grid operations. There are no hazards occurring. And the lines are loaded to no more than 85% capacity with voltages between 0.97 and 1.05, so the very standard range. In our second scenario, we consider a heat wave. And so in this case, there are multiple assets that are derated. So for generators, we see a 1% decrease in generation for each degree Celsius above 16 degrees Celsius. And for this case study, I believe we used 33 degrees Celsius as the threshold for a heat wave. For transmission lines, for lines above 66 kilovolts, we see a 1.3% D rate for each degree Celsius above 25 degrees. We also increase loads by 1.8% per degree Celsius above an ambient temperature of 22 degrees Celsius, and also a 0.7% D rate for each degree Celsius above 30 degrees for transformers. In the cyber attack scenario, we considered kind of a more localized attack on generators specifically. So in this scenario, we randomly disabled 10% of all Zone 7 generators, where Zone 7 kind of corresponds to Central Texas, kind of the Austin metro area. And then all of the other assets are exactly the same as the baseline except for the generators. And finally, we considered our compounded threat. So in this case, we consider a heat wave and a cyber attack occurring at the same time, where we make all of the adjustments from the heat wave and the cyber attack. So we considered 3 different metrics, the first being load shed, which is a measure of unmet demand, also entropy, which is a measure of relative diversity of grid components, and also functional redundancy, which is a measure of redundancy of grid components. And so I'll be going a little bit more through these numbers one by one. So we see during the heat wave that there is a lot of load shed, especially when compared with the baseline of 0. We see almost 13,000 megawatts of load shed and 6.5 megawatts per bus. And so what this indicates is that the derating of components resulting from extreme heat created this generation load imbalance. So next, when we compare the baseline with the cyber attack, we see that there is actually no load shed resulting from the cyber attack alone, but that our values for entropy and functional redundancy have changed. And so what this indicates is that even a minor attack on a single component can influence the underlying topology of the grid. And finally, when we look at our compounded threat, we can see that this one has the most load shed in terms of total load shed and mean load shed or per bus across all 4 scenarios. And what's interesting here is that we see more total load shed and mean load shed in our compounded threat scenario than in our heat wave scenario, even though the cyber attack alone didn't result in any load shed. So this really underscores that compound hazards may result in more severe impacts than individual hazards in isolation, and also the importance of studying these co-occurring threats as they relate to grid resiliency. And this is because kind of the impacts of these compounded threats, as we can see from this case study, can be greater than the impacts of the individual hazards alone. Okay, before I move on to stochastic programming, I'm just going to stop briefly and ask if there are any questions from the audience.
Any questions online?
Hey, Rachel, I have a
You
question.
can raise your, Leica, are you raising your hand or?
Yeah.
Oh, great, go ahead.
What types of cyber attacks were you using or simulating?
Oh yeah, great question. So here
What
we
did
were.
you say? I didn't hear.
Oh yeah, like what types of cyber attacks were we considering in our case study? So in this case study, we essentially just kind of simulated a cyber attack which disabled a group of generators in a particular zone in Texas.
Oh, so it's related to the power grid.
Yes.
Which makes sense.
I guess that's why you don't have load shed, right? Because, I mean, the demand goes down. It's not, sorry, the supply goes down, not the demand, right?
Yes, exactly. And a lot of times these grid systems are built with like some redundancy so that if a component goes out, it doesn't kind of take everything out with it.
One question, if nobody else has a question, I guess. So did you ever consider looking at this as a multi-objective optimization problem? Because you have these either moderate outages or severe outages. These could be kind of like have conflicting objectives. Right?
Yeah, so that's a great question. So this LDRD does have like a multi-objective focus as well, and that's like part of the future work plan.
Okay.
Yeah, thank you.
Just curious. Thank you.
Okay, so before I move on to day-ahead scheduling of generators, I just wanted to provide some background on stochastic programming. So stochastic programming is an optimization framework in which some of our problem parameters are unknown but are assumed to follow a certain probability distribution, and our uncertainty is represented by what are called scenarios. We also have non-anticipativity constraints that ensure the first stage decisions are independent of our scenario outcomes. And so essentially, no matter what scenario here is actually realized, we're going to be making the same first stage decision because this is a decision that we make before we know which scenario is going to be realized. So in the context of power grid planning, we often see stochastic programming used in unit commitment and economic dispatch. So essentially in unit commitment, what we're doing is in the first stage, so before our uncertainty unfolds, we're deciding a day beforehand which generators we want to switch on and off and at which times in order to meet demand. And then in our second stage, our economic dispatch stage, after our uncertainty has been realized, we're essentially deciding which of the generators that have been switched on are going to output how much in order to meet demand at minimum cost. And so the motivation behind using stochastic programming is that it yields this kind of convenient block diagonal structure, which makes the problem easily decomposable. And so you can see in this figure on the right that we can decompose the problem by scenario. So some challenges associated with stochastic programming, especially in the context of power grid planning, we often have integer or discrete variables in the first stage. So this makes the problem pretty complex and it's generally NP hard. And we can also encounter the cursive dimensionality oftentimes as we increase the number of scenarios or the number of variables. So one potential solution to this is decomposition because we have this convenient block diagonal structure where each subproblem can correspond to one scenario. And so I'm going to be talking a little bit about how we apply stochastic programming to the problem of accelerating algorithms for day-ahead scheduling of generators. And so first I'm going to be talking about our multi-fidelity scenario bundling methodology. So first, starting with multi-fidelity modeling. So this refers to using multiple models of varying fidelities of the same problem to try to kind of balance the trade-off between realism and computational tractability. So oftentimes we see that low fidelity models are relatively tractable but inaccurate, whereas high fidelity models tend to be relatively intractable but highly accurate. And so the goal with multi-fidelity modeling is to kind of try to leverage the benefits of both to obtain a high quality solution in a reasonable amount of time. And with scenario bundling for stochastic programs, this refers to the grouping of scenarios into these so-called bundles. And so in stochastic programming, instead of each of the subproblems corresponding to a single scenario, instead we have each subproblem containing multiple scenarios. And so the trade-off here is that each subproblem is more complex because it contains more than one scenario, but it also decreases the total number of subproblems that actually have to be solved. And so with multi-fidelity scenario bundling, essentially what we're doing is putting scenarios of varying fidelities into the same bundle. So we can see in this figure on the right, this bundling by similarity scheme essentially will group each low fidelity scenario with the closest corresponding high fidelity scenario. So then each of these bundles or each of these subproblems contains one high fidelity scenario and one low fidelity scenario. And so we apply our multi-fidelity scenario bundling methodology to this algorithm called progressive hedging. So progressive hedging is an algorithm for solving stochastic programs that's pretty simple to implement. So essentially, we just initialize the problem, we solve each of our bundle subproblems, and then we can calculate kind of an aggregate or consensus solution to those bundle subproblems, through which we can compute weights for each of the bundles. And then if a termination criterion is met, then we can terminate. Otherwise, we loop back around to solving the bundle subproblems with the new weights that we just computed. So the benefits of progressive hedging, other than it being simple to implement, are in its flexibility. So oftentimes stochastic programming algorithms will only allow discrete variables in the first stage. But with progressive hedging, we can actually have integer variables in the second or even third or fourth stages. And also with progressive hedging, multi-stage extension is much more straightforward than other stochastic programming algorithms because this is kind of a general algorithm for multi-stage stochastic programs. Whereas with, for example, Bender's decomposition, that is pretty tailored to two-stage stochastic programs. Some drawbacks of progressive hedging, though, are that it is a heuristic for problems with discrete variables, which oftentimes with grid planning problems, we do have discrete variables. We also don't have any convergence guarantees, and then so with progressive hedging, you oftentimes have to implement either your own heuristic convergence methods or your own speedups to make sure the algorithm converges. And so a key question we wanted to answer with this methodology is, can we leverage multi-fidelity modeling and scenario bundling with progressive hedging to procure kind of timely, high-quality solutions to grid modeling problems? So we've been using Pyoma, which is a Python package for formulating, solving, and analyzing optimization models, developed and maintained here at Sandia. And we've also been working on building up a Python library, currently called ForceLib. We may change the name of this, and we're planning to integrate with Pyoma Contrib. And so we applied our multi-fidelity progressive hedging with scenario bundling methodology to a unit commitment exemplar. So here we used RTSGMLC, which is a commonly used test case for unit commitment and economic dispatch. So this contains 73 buses, 158 generators, 120 lines, 48 hourly time periods, and a few kind of tens of thousands of binary and continuous variables. And so we applied this to two sets of problems. So the first problem that we see here, we took scenarios from the month of November. And in our second problem, which is in the next slide, we took scenarios from the month of March. So I wanted to point out first, so kind of on the table on the left, these bottom two rows here. So the LF stands for low fidelity, and the HF stands for high fidelity, and EF is short for extensive form. So essentially these two rows are just solving the low fidelity problem and the high fidelity problem without any decomposition, so just directly solving the optimization model. And what's interesting here is that between the low fidelity and high fidelity extensive form, there isn't a huge difference in solution time, but there is a massive difference in accuracy. So we can see that even though this is just a 4-minute difference, we see an objective error of over 900% for the low fidelity model. And then these three rows right above it, so multi-fidelity similar, multi-fidelity dissimilar, multi-fidelity random, these refer to our multi-fidelity scenario bundling schemes. So we used similar bundling, dissimilar bundling, and random bundling schemes.
Why is the low fidelity model not much faster? I mean, is it because like it's so inaccurate that the optimization is doing crazy things, or it's not low fidelity enough?
Yeah, so that's a great question. So this is something that we have also been working on trying to figure out for this specific example. It might depend on the scenarios that we used here, because in the next slide we use scenarios from the month of March instead of the month of November, and there is a much bigger difference in solution time. So I do think that this is pretty dependent on the scenarios that we use.
It might be if it's so inaccurate, it's just harder to optimize.
Yeah,
So
definitely.
it goes lower fidelity.
Yeah, especially because we're also kind of applying the heuristic of progressive hedging and then this heuristic of multi-fidelity modeling, that once we apply all of those, and even if it's a low fidelity model, it's difficult to solve. But yeah, great question. Thank you. And then, yes.
You're saying it's the same number of iterations? Is that the last column?
So yeah, the last column. So here on the bottom two, we don't have any iterations just because we're solving the optimization model directly. But in this column on the right here, yes.
Oh, I see.
Yes, exactly. And then all of these up here are progressive hedging solves that we're doing, which is why they're iterations, yeah. And then kind of in the middle here, so these three low fidelity formulations. So we have one low fidelity progressive hedging with no bundling solve, And we also have a low fidelity solve with similar bundling and a low fidelity solve with dissimilar bundling. But these 6 schemes up here do not use multi-fidelity modeling. That's just for these 3 down here. And then these top 3 formulations, so high fidelity progressive hedging, again, so this is just solving the high fidelity model with progressive hedging, but no scenario bundling. And then we also solve the high fidelity model with similar bundling and dissimilar bundling, but no multi-fidelity modeling. And so what we really want to see is having some schemes kind of down in this bottom left corner. We want to have schemes that have very low percent errors. We want them to be accurate, but also solving relatively quickly. So we also want low CPU time. And so this is very promising for multi-fidelity scenario bundling because we see that all 3 of our multi-fidelity bundling schemes are kind of clustered in this bottom left corner here. Whereas with our high fidelity methods, so these are all indicated by this X, are on the bottom right corner, meaning that even though they're accurate, they take quite a long time to solve. And then, of course, our low fidelity schemes, they're not only are they inaccurate, they're also taking a long time to solve relatively. So then these are all kind of up here.
Wouldn't the multi-fidelity times be like in between the low and high fidelity times? Because they're
Yes.
quite a bit lower.
Yes,
Right.
so that was kind of our hypothesis going into it. But for this set of scenarios, we found that they're actually both faster and more accurate than the low fidelity models. Yeah. But we also have this set of results where we took scenarios from the month of March instead of the month of November. And here we see this is actually, a little bit more confusing. So here, like I said before, we see a much bigger difference in solution time between the low fidelity and high fidelity direct solves. It's a difference between like 6 minutes and over 2 hours. But we also interestingly see that there's less objective percentage error in the low fidelity model as well.
It's percent error.
Yes. Yes, so yeah, the percent error for November was quite high because it was around 900. But we also see here that, so these results are a little bit more confusing. So all of our multi-fidelity bundling schemes are denoted by these circles over here. So we see that now these solution times are kind of more what we expected, like they're in between like the low fidelity and high fidelity solution times. But we also see a really large variance in accuracy of these multi-fidelity solves. So here we see that multi-fidelity random, this kind of yellow circle down here, did pretty well. We saw that it only took like a little bit longer to solve than the low fidelity models here denoted by these stars, but that it's more accurate. So this is kind of what we wanted to see. On the other hand, we also have this solve up here, the multi-fidelity scenario similar bundling scheme, which is a little bit confusing because even though it didn't take that long to solve, we actually saw a huge percent error in objective value. And so this really highlights that there's more work to be done in this area and that we're kind of looking forward to seeing what types of problems multi-fidelity scenario bundling works best for and also which schemes are kind of the best performance schemes. And we do have these results. They're set to appear in the 2025 North American Power Symposium proceedings. So if you're curious, please check that out.
Rachel, can I ask a question about performance? So when you're talking about the percentage error and the final objective function value, does that translate to, let's say, dollar amounts? Because, I mean, I'm not too familiar with like optimization in general, right? You have an objective function. Sometimes if a percentage error is really large, but if the objective function is relatively small, you're not saving much, right?
Yeah, great question. Yeah, so with unit commitment, the objective is usually cost. So we're trying to kind of meet demand at the minimum cost possible. And so with the percentage error here, what we're really assuming is that our high fidelity model is kind of the real world model. Like that's kind of the solution that we want.
Right.
And then these percent errors are kind of based off of that high fidelity extensive form solution.
But can you translate this to, I mean, you guys probably thought about this. Can you translate this to dollars, right? Because if if your optimal solution with the high fidelity model says, okay, it's gonna cost, let's say, $1,000, and then with the low fidelity, okay, you're incurring another 30%, which is $300, right? But that's compared to another scenario where it's millions or billions, right? So that's what I'm trying to figure out.
Yeah, that's a good question. So with unit commitment, it can really depend. Like you can definitely translate these differences into dollars from like the percentage values. For unit commitment, it can vary on the order of like how many dollars that is. With expansion planning, which was like the first project I was talking about, that can be on the order of like billions to trillions of dollars. So even like a 1% difference is a lot of money.
Okay, good. Thank you.
Yeah.
So there's a question online. The username is Mamoon. So do you want to unmute yourself and ask?
Hi, this is Art Munson. I'm sort of struck looking at this graph and the earlier one that when you do the similar, I think it's a similar bundling strategy, it doesn't seem to do very well on either graph. And that was like random is better on this graph, and I think dissimilar was better on the previous graph. Was that surprising to you also? How do you interpret that?
Yeah, so that's a great question. So, kind of intuitively, what we thought from this was that if we use similar bundling, then all of the subproblems become more different from each other. And so it's harder for progressive hedging to kind of come up with a consensus solution between all of the different subproblems. Whereas with dissimilar bundling, all of our subproblems look more alike. And so it's easier for progressive hedging to kind of force those solutions together, if that makes sense.
Interesting. I'll have to think about that, but thank you.
Yeah, thank you. That's a great question.
So maybe it seems to be that there's quite a bit of spread in sort of the number of iterations that each of these schemes take, and some of them
Yes.
run into the maximum sort of number of iterations. Is that something that you're worried about, or do you expect those solutions to improve as you?
Yeah, so one thing I should mention is that here we're running serial progressive hedging and not parallel progressive hedging. And so like one of the great things about progressive hedging is that it's really easily parallelizable because each subproblem can be run separately. And so in future work, what we're planning to do is re-implement this with parallel PH to see if some of these solution times and iterations go down.
So you're running into constraints like in CPU time where you simply cannot do more iterations, is that?
Oh yeah, we could do more iterations. I think because like with high fidelity PH, for example, we were already hitting kind of 3.5 hours. We kind of were just calling it there.
It should take the same number of iterations, whether it's serial or parallel, unless you have a bug.
Mhm.
Okay, but you're saying, yeah, you capped it so it wouldn't take two.
Exactly, yeah. Yeah, thank you. Those are good questions. And then let's see. I think I only have one slide after this, so I'll go through this quickly and then I'm happy to take more questions at the end. So to just summarize some key takeaways from what I talked about today, first is that power grid planning is incredibly complex, but also very important for safety and security, particularly as extreme weather events are increasing in frequency and severity. Also, that multi-fidelity progressive hedging can accelerate the convergence of unit commitment without significant sacrifices to solution quality, but that some scenario bundling schemes seem to work better than others. Third is that compound hazards may result in more severe impacts than these individual hazards in isolation, which underscores the importance of studying these compound hazards as they affect power systems, and also that modeling these impacts is critical for security and resiliency. There's a lot of future work that we've planned for all of these projects, including the release of this forest lib software that will contain capabilities for multi-fidelity modeling and scenario bundling for progressive hedging. Also applications of multi-fidelity progressive hedging to expansion planning. So what I presented today were results on unit commitment, but we are planning on applying this to expansion planning to see if we get similar results or kind of positive results. We're also planning on extending the Markov random field generation transmission expansion planning work into other kinds of cascading weather hazards. I talked today about a wildfire followed immediately by a flood, but we can also see hazards that reverse the order of that. So we can see flooding immediately followed by a wildfire as well. And it would be interesting to see if we see kind of similar investment decisions made in that hazard scenario. And so I'm happy to talk more about this work now in the questions, or also feel free to contact me at rmalfan@sandia.gov. And thank you so much for listening.
Great. So I don't, hopefully folks can hear me, but are there any questions? Maybe we can start online because we haven't had a lot of online questions. So feel free to just unmute or raise your hand or put it in the chat. Oh, I guess we should do like physical clapping since we're here. Yeah, there we go. So any questions in the room? I could ask some stuff, but you guys already asked a lot. Yeah, I guess so you kind of answered this in your second study, but I mean, I just maybe for the first one too, I was just curious like how expensive these things are to run. So you were showing CPU times like 40 minutes to 3.5 hours or something like that. And is that, or do you have, I imagine if you have a more complex, like larger network, maybe for the whole country or something, it would be much larger. And I mean, are there concerns that this is going to become kind of intractable or?
Yeah, that's a great question. Definitely a concern. Yes, like with the GTEP MRF work, if I go back a little bit. Yeah, so each of these plans took on the order of 1 day to, I believe the longest solve was 3 days to solve. And this was a 123 bus network of Texas that we used. And so it's, yeah, I think expansion planning in particular, there's definitely a scaling concern. And that's also a part of the future work that we're planning is on making these kind of expansion planning models a little more scalable.
But at the same time, if your goal, like if you're trying to make a plan like 5 or 10 years from now, I mean, you don't need, it's not like you're trying to decide whether to evacuate a community, right? You
Yeah,
don't need the result in like real
exactly.
time. I mean, maybe if it takes like a month, I mean, maybe that's okay for the goal. There's a question about, let me ask one related thing. I was curious, I mean, the optimization problems, I think you showed it very quickly, but is it so are they convex? Like, do you have a unique solution, or are there multiple minima, and do you have to like regularize them to avoid ill conditioning and things like that?
Yeah, that's a great question. So once we introduce the discrete variables into the problem, we kind of lose the convexity, which is why a lot of time we use these kind of heuristic algorithms that I don't think progressive hedging explicitly requires convexity. But we also have in ForceLib, we're working on integrating a solver for specifically for nonlinear and non-convex problems as well.
So I think you said your name was Art. Do you want to ask your question?
Yes, hi. So I believe that people typically use a tool called Power World when they're doing this kinds of planning in industry, and I'm wondering if this is the right time to start comparing to that, or if that's something that would be out in the future after you sort out some of the other questions about your approach. Because I think it's a likely question that people are going to have when you start trying to say, hey, you should use this. This is great. You're going to say, well, how does it compare to this tool that's typically used?
Yeah, that's a great question. So I have looked at Power World before, and I believe I ran into some issues because I have a Mac and it has to run on a Windows, but that's definitely part of the future work, yes.
Fair enough. I also have a Mac and I have that same headache.
Mhm.
Other questions online? Oh, we've got a question in the chat. Let's see. So I have a hard time scrolling without a mouse. Charles, do you want to just unmute and ask your question?
Yeah, I could do that. So thank you, Rachel, for this nice talk. So I was curious about you mentioned the curse of dimensionality at one point. And first, I guess I was just curious what sort of the higher dimensionality would look like in this setting. I know you mentioned that there can sometimes be more parameters or more scenarios. So I was just maybe wondering if you could comment a bit more on that.
Yeah, for sure. Let me scroll to where I talked about stochastic programs. Yes. Yeah, so this is kind of the most general formulation of two-stage stochastic programming. So oftentimes, especially with expansion planning rather than unit commitment, we can have like a few million variables to a few billion variables and also a few million constraints. So
Hmm.
once you get to that point, a lot of the algorithms that we use, even like the decomposition algorithms, tend to not be able to converge. I think there are also, I know that there is also some work being done in like the aggregation of those constraints to try to kind of decrease the size of the problem so that you don't run into that as much. But yeah, it's definitely a challenge, especially when you incorporate the stochastic portion of it. So if you have like, for example, 50 to 100 scenarios, let me scroll a little bit here. Yeah, so these solution times, I believed here we used 8 scenarios and we're kind of coming up on an hour to 3.5 hours. So in kind of a lot of real world cases where we could have 50 to 100 scenarios, all of these solution times tend to kind of blow up.
Gotcha. Okay, I see. And then I was curious, I guess as a follow-up then, is there like so I'm familiar, for instance, with like these kind of active subspaces or like likelihood informed subspace methods where you try to reduce the dimensionality by sort of figuring out the parameter directions where there's most variance or kind of the directions that most influence um, the resulting problem. So are there techniques in this area that are similar to that, or could you use some of those techniques to kind of help reducing that dimensionality?
Yeah, that's a great question. So the first thing that comes to mind for me is kind of the introduction of cuts to the feasible region. So sometimes what people do is they'll kind of take the feasible region, but like there's a lot of that region that contains solutions that are not optimal. And so there will be some techniques you can use to kind of introduce cuts in the form of constraints so we can add more constraints to the optimization problem to kind of decrease that feasible region. And there's also, I believe, you can use like column generation for Bender's decomposition, which does something similar to that as well.
Okay, cool. That's very interesting. Thank you. Hmm.
Yeah, thank you for the question.
All right, so I think maybe we can wrap it up. I think there were some really great questions and discussion. So thanks everyone for coming. This will be recorded if you're interested or if you know someone who is interested. So please join us in about a month or 4 weeks on November 11th. We'll have William Radun's I think he's at Johns Hopkins, give a talk. He actually just sent us the title, so it's going to be multi-scale simulations of atmosphere wind farm interactions and the role of spatial gradients on power performance and wake recovery. So thank you and hope to see you again at one of these webinars.